So these are species area relationships, and again, it's just as you get more inclusive, you see these relationships continuing to go up. Here's species accumulation curves by pit trapping. So this is nice because you dig a sampler and you walk away from it for a night, and at the end of the night you come back and you see what's in your trap. Much better that, which is in some sense sampling objectively, much better that than, what did you see today and how many were there? And yet you can see, some of these inventories look to be leveling off. Actually, no, those don't look to be leveling off. You can see here's one that is, after a lot of sampling, it's starting to level off. And you're probably not going to get much above this number as far as a final species number. In this case, who knows? Could keep going, could level off. Okay? So when you're dealing with inventories like these, it's awfully hard to guess at the final plateau when your curves are so incomplete. I'll give you an example in a bit with some made-up data. Anyhow, these are just examples for you. Those inferences are not easy. Essentially, you're saying from data like this, how many species are there that never got detected? Okay, that's the hard part. So there are a couple different approaches. They've kind of settled down on a few now. But really an early contribution was by Jorge Soberon and his colleague Jorge Llorente in Mexico. Jorge has been very fundamental in development of this program, and Alex and John and Arturo know him quite well. But this early contribution was the Jorge's basically saying, we can go beyond just saying done or not done. And instead, what they started to do was to take inventory data. This is from inventories of butterflies in Peru. And so these are the actual data. And then they started fitting regression curves. Okay? And they used 3 different forms of a regression equation. And you can see this form A is kind of very disposed to concluding that there's a very big community, whereas version C tends to level off very quickly. And in that paper, here's another example that they gave. In that paper, they explored, well, what might be the best form of the regression equation that kind of best fits to how we sample things in biology? And unfortunately, notice that there's a fair amount of variance among these estimators. And then particularly unfortunately, notice that this is the same kind of matrix, but all they care about is this left edge. The first day or the first sample, they got 4 species. The second day they got 3, the third they got 3, then 2, then 2, then 2, then 1, then 1. Right? And so my curve is going like this because each day I'm finding fewer and fewer species. But notice that that's only using the left edge of the matrix. Now that matrix might look like this. Okay? Once I see a species, I tend to see it a lot. Maybe I learned the song. Okay? But all I'm saying is that this is a matrix that's relatively full. An alternative matrix might look like that. And my guess about how many species are in this community should be a lot lower. Hold on, I've got both of them here. In this situation where there are lots of zeros, I have lots of rare species, or hard to detect species. And so I'm guessing that I'm going to continue discovering species for a long time. But here, most of the species are seen most of the days. And so in this case, I'm going to guess that my curve is going to level off pretty soon. So all I'm saying is that that species accumulation curve approach is only using this bit of the matrix. But these two matrices would get an identical result if you're just using the number of species discovered per day. Does that make sense? So a really key set of papers was this work by Ann Chow. And essentially what she was doing was looking across the whole matrix and essentially saying what qualities or what properties of this matrix can tell me about, let's go back a slide, you know, this species was detected 1, 2, 3, 4 times, and this species here, species P, was only detected once. But what about this matrix can tell me how many species were never detected? Okay? There's actually a really fun paper published in Science back in the 70s where a couple of statisticians typed all of Shakespeare's sonnets into a very proto-computer. And they did some probability statistics to calculate the probability or the expected number of new words that would occur in a newly discovered, previously unknown sonnet that was by Shakespeare. The nice thing about sonnets is that they have a set number of lines and a set number of syllables. And so the idea was, you know, let's say it's 100 words. If we were to see another 100 words in a sonnet from Shakespeare, on average, how many new words that we haven't seen so far in all of his previous sonnets? So they had done this as an exercise for fun. And then in the 70s, there was a sonnet discovered that some scholars were asserting was by Shakespeare. And so they pulled their data set out of storage and they applied it to this sonnet, and I don't remember the exact numbers, but let's say it had 4 new words in it. And that was within the confidence interval of what you would expect given Shakespeare's use of words in past sonnets. So that was, you know, samples would be by sonnet and species would be combinations of letters, words. Okay? So all I'm after is that there are certainly properties of these matrices that should give us more information than just the left edge. So Chow went in and sought those properties, and essentially what she found was that if you look at the number of species that were detected 5 times, and the number of species detected 4 times, and the number of species detected 3 and 2 and 1 time, that from those numbers you can estimate the number of species that were detected 0 times, but that are present in the community. And she's a very, very competent mathematician. She was able to show that the contributions to that number are greatest from the number of species detected once and the number of species detected twice. But the number of species detected 3 times and 4 times and 5 and more and more and more was a diminishing contribution. And so Chow produced some very simple equations, those equations that I put up yesterday, that basically are estimators of that number of species detected 0 times. So we go back to my example. Here we have 1 species detected 5 times and another species detected 4 times, and 0 detected 3, 0 detected 2, 0 detected 1. In Chow's world, that's going to be an inventory that's done. But over here, all of the species have been detected only once. And so that's going to knock the probability of a species being detected 0 times way up. Okay? So these are complicated versions of Chow's equations. But if you look at this here, that's essentially the equation that I put up yesterday. And you can get lower bounds and upper bounds and estimates of variance. Okay? More recent work, and I don't know these indices as well, have developed these incidence coverage-based estimators. Maybe Arturo understands the differences better. But they're alternative estimators. And I'll admit my laziness, but all of these estimators are now implemented in a package called Estimate-S. And so that's very convenient for developing kind of all of these estimators simultaneously. And all it takes is a matrix like that. So then I'll go back in time just for fun. I'll show you this, but I'm going to show you a couple of comparative studies of different estimators. There's this by Walther, and then I'll show you this one mainly because it was a fun study. I was working with a mathematician, mammologist, and I was asking him, what's the best estimator? And mammalogists kind of know about these things because they do a lot of long-term trapping in single sites. And notice that we're referring to some of these earlier methods, the Soberón and Llorente work. But the real problem was we never know what the truth is. So I decided let's have some fun. When I was growing up, when we would take long road trips, our game was to count license plates of different states. Okay? So in the US, we have all of these different license plates. And the nice thing about them is they have some properties that are really attractive. If you live in Kansas, where I do, which is right in the middle of the country, then Kansas and Missouri are the most common species in your fauna. And Alaska and Hawaii or Maine are pretty rare. There's actually a surprising number of cars from Alaska. That species has increased in abundance in Kansas in recent years. Anyhow, what I did was, for several weeks in the course of my day, instead of going bird watching like I should, I would go license plate watching. And I did that in Lawrence, Kansas, and I also did that in Mexico City. So in Mexico City, you have a fauna size of 31. In Lawrence, Kansas, you have a fauna size of 50. But the very nice thing is, you know the true fauna size. Okay? And then what we did was to explore these different estimators. And so these are the three different regression equation approaches that Soberón and Llorente used. This is the truth. This is Mexico, this is the US. So you can see that the truth is at 30 some here and 50 some there. And then this is the estimator. And so what you can see is that this estimator stays very low. It underestimates the true number of species all the way out to the end. This estimator overestimates the number of species until relatively late. This estimator initially underestimates slightly and then jumps right up to the truth and stays there. So this is the Clench equation, and that essentially won in both of those cases. And then we started exploring the Chow estimator and several others. And again, we got a very good result from Chow, and from some of these others, not as good. Here's another one that underestimates. This unfortunately was early enough that it didn't include all of the ICE estimators that are in Estimate S. We did this paper a year or two too soon. And then we were able to graph essentially how wrong you are against how uncertain you are. And so the perfect method is down in low in both cases. But that really led, at least for my thinking, to a really interesting insight. And that's what I'm going to talk to you about in terms of results-based sampling. And this is just kind of a proposal or a thinking mechanism. And a lot of the time, it's simply impractical. Okay? When we went out to Mongolia, we basically were working in maybe 4 sites on the trip that I was on. But really, we had no choice about when we moved. We had supplies for a week when we were up in the mountains, and supplies for 3 days when we were at this desert site, and gasoline for only 2 days at this other site. And that was set by logistical considerations. But there's another way to approach these things,